Hello, and welcome to Aluminum Welding Inspection. That's course P10 in the Elite Welding Solutions array of programs. Today we're going to talk about the defects you would see as an inspector, as a welder, and every welder is, by the way, an inspector, in the course of your duties. The objective is to try to make you understand or help you understand what needs to be repaired and what does not. Much of this has to do with specifications. Some specifications cross up at different plants. Specific specifications that you want to apply to a job is something we can cover in different programs or extra programs. But today I want you to understand the differences between all these ways, all these different defects, and how we're going to address them. So, how we're going to do this is I'm going to give you a little explanation, and we have some definitions here. What is improper termination, for example? And after we've done this and gone through these series of the important or the highlighted visual defect terms, then we're going to go through a series of pictures, and we're going to talk about each one as you might see it. And basically, it's visual reference. This is a visual inspection. Under most cases, it's a visual inspection to begin everything. In fact, all welds, it doesn't matter whether we're talking about automotive pipes, pressure vessels, or structural, begin with a visual test. Is it in the right place? Is it the right size? Things like that. So, shall we go on? So improper termination is we have to make sure, especially with the aluminum program, and if you've already covered something to do with aluminum, you understand we have an enormous number of controls in some versions. More advanced gas metal arc welding, GMAW, or also known as MIG, more advanced versions of that have ways of terminating the weld where we can program a crater condition. Crater condition is we basically ramp the wire and the voltage down altogether, and we want to create an area where the weld has had an opportunity to solidify under control. Termination for your gas tungsten arc welding process is completely dependent on the person, how they fill their crater. This would be part of your practical testing and training. Burn through, when it comes to aluminums, is almost unheard of because, is almost unrepairable that anything gets through. Burn throughs are very serious because even though I know you're going to feel like you can fill a hole, there's no integrity to that weld whatsoever. If this happens to be an engine cradle or anything like that, there are strict rules and guidelines concerning this from the OEM perspective. There's a bunch of reasons why we would get burned through. And a lot of it has to do with location, because remember that the weld joint itself has to have both components in it. If the robot or if the parts moved a little bit, the robot doesn't know that, so it'll weld a little off location, and we might see burn throughs. Crater and cracking. So if you have a crater, you can have a crater because a crater sits below the surface just a little bit. If it has a crack in it, that's what's going to define our problem or not. So I'll show you more pictures to this later on. Melt back, where the heat from the arc has actually pushed the material away from the edge. This is common in lap joints, where one material laps on top of another, where it'll run away. Next one's end notching. I have a good explanation of that, but basically it's an unfilled edge. It's a place where essentially you could put a sign on end notching and say crack here. Like I said, there's a bunch of pictures coming. I'm going to take you through them all. I just want to talk the terms first. Porosity. Porosity is a trapping of gas pockets. Now, you can get porosity for a bunch of reasons. And it's basically it's about a 3-hour course in itself for aluminum alone, just to go through all the reasons and all the conditions of porosity and evaluating porosity. But when you can see porosity, when porosity is visible in aluminum, it's a pretty serious situation because most of the time, most of the porosity is down trapped because aluminum solidifies very quickly. And most of it's trapped at the bottom. If something makes it to the surface, that's pretty serious. Most most specifications say if a hole is visible and it's a 1/16 of an inch or larger, 1/16 or larger, that's immediately a repair. And we'll talk about the repair procedure in a little bit. Undercut, I have good examples of undercut coming up. Basically, the material's been washed away a little bit. And the toe of the weld, where the weld intersects with the base metal, has a little bit of a groove in it. Now, there's maximums. I mean, when it comes to the depth, we have gauges we can use to measure it. If you're a structural company, you would probably have depth gauges to make sure that undercut met a certain criteria. They actually make good gauges for it. And of course, we could stretch out a tape measure and talk about whatever the length is, right? But for most cases in automotive, it's a visual inspection, and we'll have to determine whether or not this is good or bad or whether it requires repair. Note that I don't know any spec out there, or I don't know any prudent engineering company that would say you could have any undercut within 10 millimeters of the end of the weld. This undercut that shows up right at the end of the weld or a poorly finished crater can propagate a crack from that weak point and run it right down the heat affected zone, the area right beside the weld. Insufficient throat is the next one. In insufficient throat, basically the weld's too small. This could happen a bunch of reasons. This could happen from a robot, but most of the time, insufficient throat is from a person that's not welding with the correct travel speeds or parameters. The next one, insufficient leg, just means the weld isn't big enough and it has to be restored. Most of the time with robotic welding, we'll get a little bit of off location. So the weld will be up more on one side than the other. Usually a bit of a fixturing challenge and sometimes a parts cutting challenge. Whatever the case may be, reprocess people would be, or welders would be responsible for restoring that insufficient leg. Okay, the actual visual inspection side of it. Let's talk about, and again, I'm going to stick with terms here. I want to talk about terms that I'm going to use over the next half hour or so to make sure we're all on the same page. So the toes of the weld, the toes represent that area where between the base metal and the weld metal, that one spot right there. Now, as a visual inspector, you need to know that this is the most, let me back up. As a visual inspector of aluminum, especially, you need to look at the toes of the weld. This is a common place to look to see how the heat flowed into the material, where the transition point comes. And these toes tell us so much about a weld, and especially about aluminum. This should never roll back, for example. It should never look like a if I can just kind of do it with I should never roll away from the edge like this, right? We should always see a smooth transition of material between the base and the weld metal. Now, so the toes represent the important part of the face and of the front of the weld, and the face, of course, we're looking at the face for the shape. We're looking at the face for signs of porosity, cracking, anything like that. It's quite common that you will see cracks that will start to develop and maybe pass back a little bit this direction, right? You can actually see the crack in there. Make sure you speak to your supervisors or team leaders if you start seeing any cracks that go into base metal. I'll tell you right now that they're going to take that very seriously. If I'm talking automotive people right now, if it happens to be somebody in an automotive production, stop everything if you start seeing cracks develop. Something's changed inside the process, and it's something usually very serious. If you've made a whole pile of these welds and all of a sudden it's cracking, it could be base metal issues. It could be a contaminant on the material. Please don't just try to push through it. Make sure that the controlling people around there who are responsible for the welding know that this is happening. So the next one, the theoretical throat. If you draw a line from toe to toe and make a line there, and then you go in here right to the root, the bottom of that weld, before the material was melted away, that's referred to as the theoretical throat. Now, this is for your quality people. This is probably more so for your quality people to understand, but most do understand what the theoretical throat, and we're going to add something to this right now. We're going to say the effective throat. This is also known as actual throat, where The base remains the same, toe to toe, and then we add the depth of penetration. If we add the depth of penetration, we're good. Now, there is never been data that's ever supported having more penetration down here is better. It doesn't make it any better if the penetration's deeper. This isn't a pressure vessel. This is actually a fillet weld. It's a structural weld. So it doesn't have to go right to the bottom. There are many specifications that say we have to have a certain depth of penetration. And if you remember from the previous slides, if you've had a look at the previous presentations, I talked about how the base metal and the weld metal have to homogenize. They actually borrow, the material itself borrows a little few of the properties to try to keep the properties of this material as high as they can, the properties that give it strength. So that's why a depth of penetration is important to the process. The next are the legs. There's a vertical leg and a horizontal leg. When it comes to the legs, the size, now if it's a company that use fillet sizes and they have to use fillet gauges, so be it. If it's a visual inspection, for example, for an automotive company, these sizes are visual and you need samples available to you to inspect. So if I'm an inspector and I walk up to you and you're repairing a leg length, I'm going to say, hey, how did you know to fix that? And you're going to say, I have a visual representation of this product over here. I know what the sizes look like, and any concern whatsoever will get me to evaluate it further and decide if it's got to be fixed or not. And that's all we're looking for. Remember, for automotive, it's a visual inspection. And the last but not least is reinforcement. Reinforcement's the bump. That's the bump in the weld, how high it is. Now, it's not a problem if you have reinforcement, but if we get a concave weld, a weld that's very low like this, a weld should be flat at least. We don't want to start getting into welds that look like this. If you start seeing welds that look concave, this is convexity when it's out like this. This is concavity when it's down like this. If we start seeing a lot of concave welds, that would be something to actually bring up with quality that this is happening. Again, especially because we're talking about aluminum right now. As we start to lose our throat, as our throat starts to get smaller, it changes the theoretical throat. It changes the effective throat. So we start to lose strength as it drops that distance. So here is when I've talked about this before, and I've talked about the strength of a weld and how far that weld is away from you when you're looking at it. And when we're talking about how far the weld is away from your visual inspection, I'm going to bring up 2 points right now. First off, everybody there should be able to see 20/40 corrected. This should be the criteria for anybody becoming a visual inspector because it's a visual inspection. Nobody's expecting you to grab a magnifying glass and go through it. My friend here has got a nice distance. He's showing a good distance away from the part that he should be able to look at it and evaluate it. As you go through your components and you've learned how many welds you have to inspect, you should be looking at them, and I don't expect you to crawl all over them. I expect you to be able to see whether they're good or bad from a decent place. I always recommend vision tests for anyone who does visual inspection to make sure that they can see pretty clearly what they need to do. I've had numerous problems with this over the past where people can't see or they don't wear prescription glasses as part of their regular work day. You regularly would need them though. So I just want to make the point is without the aid of magnification is actually a wording right from almost every automotive spec. And this is an automotive application. And without the aid of magnification means that you can look at it from a distance and know if it's good or not. If you got to crawl on top of it, now we're simulating magnification. So let's have a look at this scenario where something gets looked at. with aluminum weld. Now, this is an aluminum weld that was executed, and it makes it to you for step 2, which step 1 was putting the weld in. Step 2 is the examination of it. This weld started here and went around the corner in step 2 and did a termination maneuver that's very common in automotive, where we create a weld that's basically the start and the beginning are almost the same. And this one's very well done. And then the weld comes to the end and it actually comes back a little bit and finishes and terminates on top of the part. Now, you'll see the middle of this has got a little bit of a meniscus. It's got a little bit of a dent in it. That is typical, but it's still a sound crater condition. There's nothing wrong. In fact, that's an excellent weld, and I know it would cross section very well. But the idea is to have a close look at it and see what you see. Do you see any cracks or anything, right? Then if you have any question at all, take a wire. You've got wire brushes. Almost everybody's got a wire brush, which, by the way, is only used on aluminum, on clean aluminum, right? It doesn't touch your barbecue, but it gets a brush if you want to check further. Sometimes you'll see little streaks in the puddle, as in the crater, as it's closed, and you might think to yourself, is that a crack? Give it a little brush with a wire brush and see if it's okay. That is that tiny little speck in the middle there would be more than acceptable in a crater condition, because it's literally not even part of the weld. The person's done an excellent job in programming this one. And then you say if it's acceptable or not. And this is a glance. This becomes a glance. Now, before I move on from this one, I want to make one very important point. If your responsibility to automotive is to stand there and you're essentially a quality gate and a rework person, you're an inspector first before you're a welder. But if your job is to do that, you should know your station. I have to go and do audits on companies all the time. And the first question that I ask everybody when I walk up to them to see if they know their station is, how many welds do you inspect on this line? So you're standing right here. You have a responsibility to how many welds. And I always want to know that, because I want to see if they understand how many welds, because that's an important part of figuring out whether everything's in place. There could be a skipped weld here. So I've had many people say to me, I don't know. And I have to go back to the office and say, if there was a weld, they say they don't know. How could they not know? There could be a missing weld and we wouldn't even know. My point is, from all this, take an interest in this. Take an interest in your station, at least for a while. I know it becomes mundane, and I take my hat off to the people that can do reprocess like this. It's challenging. But take a moment to understand your station. Understand what you're fixing. You will understand your responsibilities for fixing, but how many you're fixing. Watch when there's consistent problems, right? Don't keep making bad parts all night and welding just because you like to weld or just because you think it's okay. Make sure you alert people to certain situations, especially with aluminum, and especially if you're new at it. Here's a crater cracking condition. Now, I've said a couple of times, but this is a perfect time to talk about it. I've said a couple of times that aluminum welding is a metallurgical solution. In this particular case, and by the way, this is that white area where we're stripping the oxide layer off. Great picture of it, right? But this is base metal. These are the base metals, and this is the weld metal that's been put in place. The contact tip, this was a gas metal process, and the contact tip failed about here, and it started to hold the wire back, but the arc kept going. And as the arc kept going, it kept this area hot with no fill. So look at the cracks that have started. Now those cracks are there because the metallurgical solution, that 6% higher silicate or whatever the filler material has in it, whatever that composition, wasn't there to help to control the crack. The welds are far more ductile than the base metals are, especially with the 6000 series. So your responsibility on a spot like this would be to take your grinder, take your die grinder, take a little bit of this out, clean this away a little bit, and create a proper termination. The question, the moment I have for you right now is, and I'm going to throw a question at you and pause and let you think about it. What direction would you travel? Would you travel this way or this way to finish it off? This way or this way? The correct answer is to start here. Start closer to your edge, get it hot, and then weld back this direction, because you're welding to sound metal. You're welding, and your edge where you start off will be nice and clean. It'll look like the beginning. So it'll be like a beginning here and a beginning here. Again, trying to respect that crater condition. Here's a termination that could give you a little bit of a trouble, because here's a termination that happened too quickly. Now this is actually an outstanding photo of somebody's programmed this, and they've done everything correctly with respect to location, with respect to how far they traveled. And notice they actually went up a little bit. That's outstanding. This was a technique used by a friend of mine, Anthony Siaco, many years ago in a project we worked on. And he had a 5-part process of doing this and making this termination as clean as possible. Now, in this particular case, even though as perfect as the weld is in almost everywhere, where it started to stall a little bit here, but you can see this contact tip was giving us trouble. It held the wire back. There was a quick fuse right there, but then it started up again here. And then but when the weld wire and voltage were trying to shrink, and that's what happens right here. The weld wire and voltage tries to shrink, and then the wire stuck again. And then I just had a bit of an arc, and I didn't get my fill. So there goes the robot. It left it sitting here without fill, without any protection. I didn't have a chance to execute its problem. So when it did, you can see that it left us a crack. Now this is a nice repairable crack. It does not extend out into the base metal. This one would require a little bit of die grinding. And if you look in the center here, interesting, because it didn't have the fill, it was left very hot. There is some black oxide that's formed right there. I have a good picture coming. It's probably one of the better pictures of oxide you'll ever see. But there's a chunk of black oxide in the middle. That's key. That's a key repair. That's got to get fixed. Remember that black oxide that's formed from the aluminum, the molten aluminum, being exposed to oxygen. So when the robot was gone, the gas was gone, and it exposed it just a little bit, because the center is the last part that solidifies. But as it shrank, it didn't have any fill. Like we said, the wire had stopped, and of course it split. These splits come from this weld material shrinking and having no material to feed it, no material to compensate for it, so it pulls itself apart. But a die grinder fix, a little bit of a termination fix on that one, and it is ready to go. Now this is 6061 aluminum. Now 6061 aluminum is, I'm going to say it again, metallurgical solution. So we had a problem one time where there were some cracks. And these cracks were starting to develop on the inside. And this was a key problem, because it broke rules. It broke rules in that the first rule is you don't put weld where weld is not supposed to be. And there was some cracks developed from the other side that actually put a little bit of a crack along here that would have said, scrap it. But some people took it upon themselves and tried to put a weld on the inside of this. Now the weld on the inside, there's actually something that slides down inside of this, so that it had to have clearance. So somebody thought, I'll just put a weld on here and I won't add filler metal. And you have to add filler metal, especially because of things like this. This material cannot fuse to itself. You can't take 6061 and weld 6061 with a 6061 rod. The material can't take all this heat, and it has all kinds of problems. We need that homogeneous mixture of a different type of filler. We talked about it before, 40-43, 53-56, 55-53, and like I said, there's about a dozen or so more after that. The next one is an oversized weld. It's a bracket that went in place, and when the bracket closed, when the weld closed, uh, the bracket and this big lump of material here pulled the heat out of it very quickly, and the person, and this was done by TIG, and the person did not add filler material and terminate with their finger control or their foot pedal at the correct rate. Again, a quick look at the cleaning action going on here, caused from the AC from previous courses. But anyways, this just closed too quickly. The weld's too large anyway. It's way too high. This is way bigger than call out. Call out on this one, I can't recall exactly what it was, but it certainly is much higher than it needs to be. Here's a person that tried to slap a weld on top of a weld instead of trying to take some of that weld out. I'll give you an example of what should have been done on this one in a couple minutes. But again, even though their efforts were clean and pure, trying to get this nice big weld in place to make sure it's stronger, their termination requires a little bit of work. And this is a typical crack that you would see. I just thought I'd pull one in close so you can see how they look. Now this is a picture that I took years ago of an area where a welder, this is a piece that's cut out, and it was longer, and the welder had taken the TIG torch and done the worst possible thing that you can do with a TIG torch. He got the area of the aluminum, the entire area, really, really hot. And what this did was it brought the whole material up to the point where it was starting to absorb oxygen. Now, aluminum loves oxygen because it's trying to make those vitrified aluminum oxide, like a grinding wheel, is trying to form that aluminum oxide, which is really, really hard. Now, this was a very interesting picture in that it's actually gone to the University of Waterloo have this picture that they use because it actually was interesting, and it shows the transition point where the material is getting so hot it's starting to pick up oxygen and form rocks inside the aluminum. So we were able to take it and pull it apart. And a good friend of mine pulled this apart and said, "You got to see this." And it shows all the formations. Clearly, this was a spot here where there's so much advanced formation of aluminum oxide that there's actually big black chunks. This was just beginning. So it's a great picture to try to understand a little bit about how this material is affected. My point, you don't sit in one spot with a TIG welding gun. You can't just sit in one spot and get it hot and get it hot and get it hot. You're causing trouble. You're causing deficiencies in strength as well. You'll start the annealing effects of too much heat. Not only that, we start to pick up oxygen. The material, that is aluminum, is very finicky that way. Here's a typical burn through that would be a scrap bin under almost any condition. If memory serves, this is 5053. It's a stampable aluminum. And this is 6061, a material called T5 or T6. The T represents the thermal conditioning of the material. Now, why this is going in the garbage is this is too much to fix. Even if you could get a piece of material and spend hours, but you couldn't get to the other side of this, you are going to be in a lot of trouble trying to fix it because there's big drips on the other side. Now, skilled people with TIG welding can look at me and tell me all day long, and MIG welding people, "Bob, I could fill that." I don't want you to fill that. That's the point. Your quality program does not want you to fill that because that weld has no integrity whatsoever. If they have a field condition and that cradle comes back, or God forbid if there's an accident, that's going to hold nothing if you bridge it with a little bit of 4043 or 5356, and that is try to fill it with a bit of a bridge. And here's the other thing too. Supposing you did. Supposing, oh yeah, I'm going to challenge myself tonight. I'm just sitting here. I'm going to fix this one. Not only is there no base metal, which is what I'm worried about underneath it, there's nothing there. But We already know that liquefied aluminum, if it's not protected by argon, is going to develop all the oxide. That's what happens on the inside of these welds. It just looks like a black rocky road on the inside, and it will have not only no integrity, but I just need you to know, and we all need you to know, that if you think you can hide this, if there's an incident, you can't. They know what you did, and they know everything you did, but just by the cross section. Somebody has fixed this, and it's been a complete burn through. And by the way, a burn through that long, there's no circumstance in the world under an automotive condition a burn through that long would be acceptable anywhere that I've ever seen in a spec. Now, this is a condition called end notching. We've talked about end notching a little bit in the beginning slide. I wanted to define it. Now, whenever I see a condition where there's end notching, I always think to myself, yes, I get it. There's a weak point there. But every time I've had a problem like this, I've always gone back to the drawings and found out if this weld needs to be continuous all the way along. This is basically end notching because we got the arc so close to this edge. If this doesn't have to be a continuous weld, I would start I'd start a weld going this way, and I'd start a weld going the other way. Things we would do from design. But until we get these things nailed down, and there's some conditions, and as much as you think, we can perform miracles, we've done something wrong. If from the engineering perspective, if this happens, it's going to happen sometime, especially with aluminum. And because only small changes. We all know how steel affects us. We all know that steel changes a little bit, and the fit changes a little bit. Well, those fits and those locations have to be far more accurate with aluminum. So little things like this are going to show up, and they are and would be that something like this your responsibility to fix. Because see that's you put a sign on that, say crack here. That's all you're telling that right there. If you wanted to find a way to make that weld fail prematurely, you could take just a hacksaw blade and cut down into it in the same fashion. And it would take this heat affected zone. This is the area right beside the weld here with the heat affected zone. And it would just split right down there very, very quickly. So that's part of the problem. Not only is it notched, but it's notched leading right to a heat effective zone condition, which is just a little bit softer. Here's a couple of decent terminations. This side's all right. I don't mind the way it's been done. Don't like this in here. It's a typical bracket you might add on to something. I don't like the condition in here. This is where your TIG welding skills can come into play. You can do things with the TIG welder that you can't with the MIG welder when it comes to doing reprocess work. There's a lot of companies, I want to do MIG welding for my reprocess work. Well, congratulations, but you're not fixing anything. It'll just lay on top. Because now there's a weld in place, we need more than just heat. We need local heat that is on a particular spot, and we need heat without wire coming, so we can blend these welds together a little bit. After you're done, once you become proficient at gas tungsten arc welding, you can terminate these in such a way that they are done. They won't require any more buffing or any nonsense like that afterward. You will be done. Now here's a typical weld that's had some gas problems, I believe, and you see this often where there's become turbulent. Now, see this edge that's coming like this? There's a bunch of different reasons to have that, but in aluminum, often it's caused from dirty nozzles. Now, it's caused from dirty nozzles because dirty nozzles build up and the gas starts to come out erratically. Sometimes the gas will come out if the hole closes up, if it's not reaming properly or anything like that. It'll cause the gas to come out either with greater velocity or with turbulence. And when it comes out like that, it's commonly going to get picked up on. It picks up some air. Now, air we talked about is 21% oxygen, but it's 78% nitrogen. And I want you to understand that nitrogen, if it happens to make it into the puddle in the smallest amount, it actually creates a much more powerful gas. We've actually been experimenting this for the last 10 years in something called nitrogen doping in argon to try to give it a little more power because we know it happens. Now, one of the telltale signs is this undercut right here. So this nozzle, this is one of those things, this nozzle needs cleaning. This is not a thing you're going to sit here and wrestle with all night in your reprocess station, if in fact that's what you're doing. This is not something you're going to wrestle with. You're going to stop, and we're going to get somebody over, and we're going to get that fixed, because that will only get continually worse. And remember this always. And now you can almost use what I'm about to tell you across the board on every single welding process. We want to weld it once, hot, and fast. There's only a few exceptions to that everywhere in the welding industry. The quicker you can liquefy a material, homogenize a material, and have it fuse back together and solidify, the better. With, like I said, only a few exceptions. Now, this is clearly a deficient weld. There's no need to dwell on it too long. But this one is really nice, and I wanted to point it out because you don't always have to grab, especially if it's a reprocess, you don't always have to grab brushes and cleaning and everything else before you get started. With the AC process, you could just dive right into this and start a little bit of a TIG weld right there and weld across there, and you don't really have to do anything. As long as that's, and this is just, actually, it's much cleaner than it looks. This is just a little bit of a shadow. But because of where I've taken the picture from. But this area right here could get a little bit of reprocess, and it's done. It's a more than acceptable. Just because it has this piece in the center here doesn't make it not acceptable. The actual button that's created, I like to use that term. That was mine. The actual button that's been created looks in good shape and good form, and it's quite thick. The other end looks fantastic. There's nothing about this weld that scares me. It's just there's a little bit of, let's just say it doesn't meet leg length, right? Because that's kind of what's happened. Now, the other part about this is, I wonder why. I wonder why this area. And usually it has something to do with, so often, especially if it's consistent, it's the angles of the torch. So if you see an area like this, and this is your skills as a reprocess person, if you see something like this happening consistently, you need to tell the robot techs so they understand every time the robot gets in this position, it's binding the wire. It very well could be binding the wire in such a way that just holds the wire back. And if the wire is being held back, it just makes the wire a little bit starved. And then it changes position, it loosens up, and then it welds normally again. So watch out for things like this. It could also be just because the contact tip is starting to die, and it started to stick a little bit, and then it cleaned itself up. Here's a termination, and I always like to put this out there. It's a crater. It has no crack. It has very little oxide in it, even to be concerned about. It comes to the edge of the weld. It's not exactly the right choice, to be honest with you. You would always start on an outside edge. This is the outside of the component, but you would always start on the outside edge and weld in. So something happened though at the crater condition where we were trying to execute a crater fill, and you can see the contact tip was dying because it ended up spitting out a little bit of material here at the end. Now I just want to say that this is one, just because it's out on the outside edge, that I would fix. However, there is, by specification, I just want to note, nothing wrong with that crater, because it doesn't go into the base metal. It doesn't it doesn't have a pile of oxide in it. It's got a few areas on the surface. Like I said, no cracks, and it doesn't dig in. There would be no problem with it. Only because, like I said, it's on an outside that I would make sure I'd fill that up. And this is something called melt back. You see this often in aluminum, where the material runs away. Now, if you see a lot of melt back, there's a condition that happens inside your welding programs, and we got to make sure we have good torch angles. There's torch angles to be conditioned, and there's also something called arc blow. Sometimes the robots do this. Now, as as reprocess people, again, that's what you're doing, you guys are very valuable. And I can't stress this enough, to tell us about little things like this. And this is part of the communication. Is also part of the course, is saying, I want you to throw a flag in the air when you see something like this happening in any level of consistency. Because sometimes welding cells build up magnetism and the arc will start to blow in different directions. Sometimes it happens, most of the time it happens when the cells running really, really hard. And these are things I want to make you conscious to, because it's not your job to sit and fix everything. Please, I want you to understand that you are a trained observer here too. And looking for patterns will really make you stand out with the company, because that's the type of thing that the pros are all looking for, somebody who takes that type of initiative. Here's a weld that was completed. It was done by the robot. There's nothing from a specification point of view that's wrong with it. I don't like the end of this. Now, notice that this is done in one pass. Now, I've had this happen where people have started to see this area here and they've started to fix it because it's not a complete weld. This is for you to speak to quality. I don't want you welding anything unless you have to weld it. You're not doing it the strength any favors. So if you see a situation where, oh my God, this could be called out as 3 separate welds. If it's called out as 3 separate welds, it's okay to have this, because the length of the weld will probably be from about there to there. Now, again, border samples. Your quality department is going to build you a part that's going to be pristine. It's going to meet every criteria, from welding to locations, quality, sizes, everything for you to reference. So that's where you'd probably find this information. But again, if you don't know, that might be fine, just leaving it the way it is. Crater condition. Well, as long as the crater is not digging into the base metal, we know that. And as long as the length of this weld meets the criteria without the size of the crater, you're good. The crater becomes part of the weld size when it becomes part of the weld length. The weld length is not the responsibility of a reprocess welder. The weld length is a responsibility of quality and production, maybe even maintenance, whoever is programming robots to do audits, documented audits once a week to make sure we're not over welding or, of course, under welding. Some companies will add quite a bit of extra weld to make sure they've got it all good. And if there's a problem, then they run back to the fact that it's over welded. Well, this gets costly when you're making a lot of parts, especially with aluminum. There's a lot of consumables involved in putting down a couple of pounds of aluminum, including the gases, consumables, all the rest. Now, the 3 important considerations for termination. This particular one has lost its volume, right? We have to maintain a certain amount of volume. Now, this does not dig into the base metal. This is, again, the wire was going down and it started to stall, and it completely stalled. And then when it got to here, the person changed the direction using a particular technique and came back up on top. This is deficient in size. Now, the question is, and this goes back to your component now, the one you're welding. You need to know from your border sample, is the entire length of this weld all the way down, is it part of the full length of the weld? If this weld is already long enough up to the size where it was the correct size or met the standard, it would be fine. If you required this, and in this particular case, it requires to have the correct size, it would be unacceptable. So it needs some reprocess. So a TIG welder was used, of course, got it hot and brought it back and started, of course, welding from the end and bring it back up on top. Finish from the ends. Start here if there's an end condition problem and weld towards this piece, right? There's no porosity, there's no cracks, but we don't have fill. Here's a chunk of oxide. It's an interesting picture, and I'm just going to share something with you. So this is a weld that started here and went back and created what I consider to be a perfect termination. It utilized the heat from the area that we just welded, and the current was actually ramping down while the crater fill was being done. You rarely see one that good. But it caught a little bit of, there was something wrong. I don't know if it was gas flow. You can see it's picked up some oxide, right? I don't think it was dirty material, I can't say, but a bunch of oxide formed right here. Now, I just want to point out the fact when you see that black like that, there's a couple of points. First point, you can't weld that. That's so hard, that oxide. You don't even have the capability with your TIG torch of getting oxide after it's formed hot enough to melt. And if you did, it would not melt back into the aluminum. It cannot be just added to when it comes to seeing a visual chunk of oxide in front of you. And I do want to say this, if you're going to grind that weld out, take caution, because when I do practicals, using that die grinder is part of my criteria. And everybody should and needs to be able to and practice with a die grinder to make sure that you never, ever, ever touch base metal. That die grinder should never touch base metal. A quick story, when I was a younger lad, my journeyman used to paint a little welded part, and he'd say, I want you to grind that weld down, and he'd paint it so he could see if I touched the heat affected zones. And it's not a bad little way of testing it, but it's pretty much easy to see if you get it bad as well. So getting that out of there will take a fair amount of skill with a die grinder. It might even take a different type of die grinder than you have available to you. But you can't get that hot and fix it is one of my main points here. And all this on top, excuse me, should be setting off a few warning bells about the cleanliness or maybe how dirty that nozzle is. And remember, even though it's going to a reamer, you think, okay, it's going to a reamer. And somebody might say, it's going to the reamer, it's okay. All the spatter I'm talking about that accumulates way up inside, right around the diffuser and the diffuser cover if you're using Feronius. So it's got to be cleaned out a little bit because we could be creating some issues. Here's a cross section that was put in place, and I brought it out because it has a cold area in here. And this is the condition I was talking about from a visual perspective. When you see a weld that rolls back like this, that should set off warning bells that this area requires some attention, this area right down in here. Because if you're getting this rolling back, your heat input here is very low. It will only stick to the areas that are hot enough or liquefied. This means you've added too much filler material and it's built up based on what we need. So the leg length would be deficient, and the leg length is going to require restoration by adding it right in here. Again, referencing your prototype, your sample, your shop floor sample for size. Now, this is a condition we refer to as undercut. Now, undercut is probably, especially when it goes along an entire area like that, the absolute worst thing you could possibly do, the worst thing you could have. Because you may as well put a sign on it that says, crack here again. We've created a weak point. Not only have we created a point where the material, the base metal is compromised, this particular one is a weld with excessive reinforcement. So that means there's a lot of extra stress on it. And it's hollow. It's hollowed right out and thinned the base metal. So the base metal thinned. We've lost structural integrity because of it's so thinned out. The weld, it's typically off location. Now, what's caused this is not clear. I have a suspicion that there was a dirty nozzle involved again, because we've ended up with a lot of black starting to form, and that black represents the aluminum that's kind of flying around inside the puddle, around the puddle, the argon that's flying around. It gets trapped in it, and then it gets outside the argon shield, hits the air, and turns black. Just the same way we form aluminum oxide, and it looks black. Now, you have to look at your own specification when it comes to this one. However, there should be no undercut in the first 10 millimeters, last 10 millimeters. You should not see any undercut here or here. Now, no matter what the specs say, and the specs are very clear and that there is something allowed, rarely do you see anything more than 25%. This one requires rewelding. It requires a nice TIG pass to go all the way across with a proper termination about there. And we'll give a good look to that while we're there. But this is not something you're going to sit there and fix all night. This is something that there's a problem with the gun and needs to get addressed. No robot tech is going to program something that's going to come to you looking like that. Now, this one, I always like to throw this out there as like, what do you think happened to this one? This one was being welded with a water-cooled gun, and the water-cooled gun started to leak. I just put it in there for interest's sake. You can see how the aluminum was literally quenched with the coolant and how it took on the shape. It was of course, it needed to be completely ground out. And I would go ahead and grind that out because the weld is all okay, basically on the bracket. We haven't even started making penetration there. Now, as I'm grinding this out, first observation, any cracks in base metal. No cracks in base metal outside of the weld zone, re-weld it. If there's cracks outside, if I look underneath this and grind it down, and I look underneath it and see any cracks, scrap it. Don't think about it twice. Here's a cup weld that was reworked, but nobody paid attention to undercut. This is the undercut that you need to pay attention to. And this undercut has to be filled. And see the way it's rolling here? This particular thing, which happens to be a cup, is a little bit thinner than the base metal, right? Especially when they very nicely gave us a little extra thickness here to try to absorb some heat because the cup's a little thin. But the welder who inspected and decided what needed to get done did not pay any attention to the cup, to trying to get this undercut in place. They were probably fearful of burning through. Under most conditions, if you burn through the cup, it's scrap. But this one was going to be scrap anyway. Comes down to your skill set. Your skill set. Now, when you're fixing something, we got to make sure we're not in a condition where we can't inspect it. Now, I've seen conditions like this show up where somebody has poured a whole bunch of material into it. Now, we go down to the plants. We go to the OEM's plants, and we have to sit there and support what we're doing. And I remember going to one time, and it was aluminum. It was not this weld, by the way, but going to one, and they said, how do you inspect this weld when you can't even see the weld? And the person had built so much weld up that it was just a great big lump. Now, what they had was what was over here on the right. That's what they started off with, and it probably had some problems. So they just went and welded it up. But it's not even a fillet weld anywhere. My point from this slide is this. The weld needs to be what they asked for. If it's anything other than that, it's sufficient. Even if you think it's more, there's no such thing as more. If I give them more, it's better. Don't think like that in welding. More is not better. More can cause us more problems than you can imagine. If when we go to the plants and they want to do a defiance test, that is loaded onto a machine and beat this engine cradle, this component to death to find out where its weakness is, they look for the ones that are reprocessed because they've been welded again. And they know that they're one of the worst, especially right beside the repair, because often the repairs are too significant. They put too much weld on, too much where they don't need it. Now, this was a chunk of oxide that showed up on top of a weld where a person had said to me, Bob, I can burn that out of there. And I said, oh, okay then. I said, let's see how it goes. So the chunk of oxide was there, and they went in and put a weld over it, and then I cut it on the spot. and found it to them to show them that the oxide cannot be melted, and you're lucky if you can even get it to move. Now, this may as well be a hole. Just because that's a chunk of oxide doesn't mean it's doing anything. If the aluminum doesn't stick to it, which it does not stick to it, you could take the oxide, you could knock it out of there like it's a chunk of stone. Because that's, to aluminum, that may as well be what it is. But in the condition you see here, that's not a good thing that I want to ship. I don't want to ship parts that look like this. We would take our die grinder, we would clean a little bit, area off a little bit, clean this area out, and then restore our weld to where it's supposed to be. So here's an idea of how to go about the process of a weld having a problem. So I've taken this one, and I've actually, the weld came to me, and it was completely off location. And you can actually see the edge of the bracket. So weld being there, seeing it, obviously in the wrong place. Further inspection says it's got to go. It's not even near in the right place. See my material? See my material? I just make sure it's not down too far, right? I can just go ahead and take the weld off. But I'm gonna when I weld, I'm gonna take some of this with me as well. And then I'm gonna execute the weld and terminate it as I would regularly see. Now, so I weld down like this, and I got to the end, and I brought it up to make sure that I have a good condition here and a good condition here. See the cleanliness of the material? That's even going to show up in your technique. Even in your technique. And then, of course, I terminated, and this is a hand termination, where I turned down the current and added filler material at the same time. After the weld, you know you're not going to be welding on it, you can take a soft disc. It's not a problem. And you can take a soft disc and you can clean this area up just a little bit, and it'll be fine. There's no call out that says you have to build up any welds beyond the toe. Remember, this bump is referred to as reinforcement. As long as you're flat or more, especially with the TIG process, you got everything you need. If you flipped around to the other side of this and you inspected it, you would have noticed that it's cracked. The control arm is cracked right through that base metal. Now, I did the repair, and I did the repair to kind of show the technique. But this cradle would be scrap if you see that. Just to give you this understanding of why it happened. And it cracked simply because it got so hot. And expansion and contraction, we already talked about it's being far more vicious than expansion and contraction. Being what it is, it pulled itself apart. It got hot, it expanded, and then cooled and pulled itself apart. And that's what it is. When it gets hot, it expands and deforms. And then when it tries to cool, it shrinks and literally has to pull itself apart. So even though I fixed that one, I looked around the other side. Oops, cracked through the base metal. Right there. Trash can. Recycle, I should say. This was another project I was on one time with an LCA bracket. And I just want to point out, and I know I've done this a bunch of times, weld does not go anywhere that weld does not call out. Your border sample, your sample on the shop floor that looks at your part, that gives you all the things we want it to be, we'll be looking after those locations, and anything else cannot get out of the plant, should go into containment, and start containment protocols immediately if you ever see anything like this at all. Even on one part, don't let it get out. There's a typical end notch. There's a little bit of an end notch right there. That would be because we've thinned the material out here. That would need some type of fix. And that requires moderate TIG skills, but very simple to fix up. And of course, I would start welding here and weld myself back in this direction and terminate somewhere up on top here, like the people have done already. There's another one that's a little bit worse. These guys are struggling a little bit with their program. They need to turn down the current to kind of bring it back up on top. So they came over like this. They came up on top, and the arc was kind of wandering on them for another reason. So Okay, thank you very much for joining me for this program, and you have a good day. Thank you. Bye-bye.